a stock price prediction. So I will brief you about what is the agenda of today. First of all, we will understand the problem statement clearly. Then we will look at different models which we can use for predicting the stocks prices. And those are moving average, linear regression, time series forecasting, and then finally we will look at the LSTM, which is a deep neural network model, and we will do a code demonstration for the LSTM model. Moving on, let's understand our problem statement very clearly. Our aim for today is to predict the stock prices of any public listed company. So what are the different data points which we can use for predicting the stock prices? First of all, we can scrape Twitter and find about the post about the company. Similarly, we can do for the Reddit post. Similarly, we can do for the news headlines about the company. And after scraping this post, we can use natural language processing and sentimental analysis to do the prediction. And another approach is using the historical data about the stock of the company. Now the now today we will primarily focus on how to do stock prediction using the past prices. Okay, moving on. Now, if you want to do the stock price prediction using the past prices, obviously the first step is to gather the information about the past stock prices. Now, what are the different options we have to gather the stock prices? Now, we can gather the stock prices using some financial websites, and there are many out there. And some of the reliable financial websites are Yahoo Finance and Google Finance. And another better approach is using Python libraries which are built under this financial website's APIs. One of those is Pandas Data Reader and another is Stalker. Pandas Data Reader is a Python library which works on the Yahoo Finance API. We can simply find out the ticker name of the company to calculate the data using these Python libraries. Now, once we have gathered the data, let's have a look on the sample data set. Our sample data set is actually a collection of of different types of prices at different dates, at a series of dates actually. Now, let's have a look on different price attributes we have. We have open, high, low, last, and close. What are these attributes actually? Well, open and low, open and last represents the final and starting price of the stock on that date, whereas high and low represents maximum as and minimum price of the stock on that date. We will be primarily using close price for predicting the stock prices because those help the most. Those are the best attributes for predicting the stock prices. Now, let's now once we have gathered these attributes and we have now we know that we know that close price attribute is the primary attribute to predict the stock prices. Let's plot a graph on let's plot a graph of close price attribute of stocks versus date. After plotting a graph, we after plotting a graph, we this is the graph how it looks like. This is actually a price versus date graph. On the x-axis we have price, on the y-axis we have date. Now, what's our problem? Our problem is to predict the stock prices. Let's give a mathematical approach to this problem. If we in mathematics we can this is a similar problem to mathematics where we have been given different x and y coordinates in the system, and we want to find the equation of the system. Once we have find the equation using those points, we can find out what other points lies on that graph or on that equation, right? So this problem is similar to the simple mathematical problems. We have been given different data points on x and y axis. Once we can calculate what's the equation of this graph, we can find out what other points will lie on this graph, right? So now the question arises, how can we find the equation of this graph? This graph doesn't look simple. In fact, at first glance, it looks like it's very random. It's impossible to predict this, to find the equation of such a graph. In fact, a hypothesis given by a in fact, a, in fact, a hypothesis given by a great economist named Eugen Fima said that predicting stock prices is actually impossible. Now, so efficient market hypothesis says that predicting stock prices is actually impossible, but it was given in 1960 as but now using machine learning models and deep neural networks, we can predict the stock prices. We can now find the equation of graph using these models. Now let's have a look on some of the models by which we can predict the stock prices. So some of these models are simple statistical models like moving average. Then we have machine learning models, simple machine learning models like linear regression, k-nearest neighbors, and support vector machine to predict the stock prices. Further moving, we have time series forecasting models like Arima, Sarima, and Profit, using which we can predict the stock prices. Then we have deep neural networks like RNN and LSTMs, which which among this gives the highest accuracy. Which among this gives the highest accuracy? We will, as we have time constraint today, we will just give a brief overview of this primitive models. Uh, we will just give a brief overview of this primitive models. We will tell you about what motivates and how we can use these models, as well as why we are using these models to predict the stock prices. Further, we will look on the graph and the accuracy which we are getting using these models, and we will see the disadvantages we are having and how this disadvantages by overcome by the LSTM model, how disadvantages is overcome by the LSTM model, which is actually a recurrent deep neural network model and which gives the highest accuracy for prediction the stock prices. And then finally we will demonstrate you the code for LSTM. Now let's have a look on the some of these models. The first model is the first model is the first model is moving average. Moving average is actually a statistical model. It has nothing to do with machine learning. Moving average is actually a statistical model. It has nothing to do with machine learning. To predict this next price of the next ray, we are actually calculating the average of the previous some n observed values. So it has nothing to do with the machine learning. Let's have a look on what accuracy and graph we are getting. So this is the graph, and accuracy we are measuring using RMSE, which is a standard way in machine learning to calculate the error. Now in this graph, the blue line represents the blue line represents the actual values, whereas the orange line represents the predicted values. As we can infer from the graph that there is a huge difference between the predicted value and the actual values. So the question is why there is such a huge difference? Because we are using mean as a criteria to mean or say average as a criteria to find the next predicted value. So whenever we are finding mean, it's actually returning the predicted output within the within the range of the previously observed values. Now let's have a look on another simple model, which is a machine learning model, and it's a very simple machine learning model which is very easy to understand. Which is a linear regression. We use linear regression whenever we have some dependent variable and there is some independent variable. In this problem, we can easily say that our stock prices is dependent on the date. So our time or date is an independent variable and price is a dependent variable which is dependent on time, right? So using this model, we now I will show you the graph and the accuracy we got using this model. As you can see, the RMSE for this model is in fact more than the moving average. And let's have a look on the predicted values and the actual values in this case. So these are the predicted values, these are the actual values. We can see still there is a huge difference and still there is a lot of error. So why this error happens? So whenever we use linear regression in this case, it is overfitting our data set on date and month of the year. So whatever predicted values are actually some of the previous values, previous value on the same date and month of some another year. So a linear regression model overfits our model. So So this thing I already told you about. Let's now have a look at time series forecasting. We use time series forecasting whenever we have been given some XYZ data versus a time. In those cases, we want to predict what value of the XYZ will be at some time, right? To understand time series forecasting, let's understand stationary graph and a non-stationary graph first. A stationary graph is a graph which have some patterns in them, whereas a non-stationary graph is a graph which does not have any patterns in them. So if I will ask you a question, if we want to predict something, which of this graph is of more important? Obviously, stationary graph, we won't be able to predict something if we don't have any pattern in the graph, right? But after having a look on the stock prices versus the date graph, we can easily infer from the graph that it's non-stationary. There is no pattern. Then how can we use this graph to predict? To how can we use this graph to predict the values? So there are time series modeling. um, there are different time series models like ARIMA, which stands for Autoregressive Integrated Moving Average. What this model does is it takes the of non-stationary graph which we have and converts it into the stationary graph which we can use for predicting this, where we can find the patterns in the graph, right? To do so, it uses the autocorrelation function which is ACF, and this ACF takes a non-stationary graph as an input and gives output as stationary graph. Now, let's have a look on what accuracy we are getting using this model. Using this model, we can see that it's far better than the previous two models. The predicted price is now showing some trend. Wait, what's a trend? What's a trend in the graph? So whenever we are using a time series modeling, we use two terms for the graph, and those are seasonality and trend. So what's a trend and what's a seasonality? So trend is major changes in the graph and a seasonality is a small changes in the graph. So if we have a close look on this graph, this there are many minute changes in the graph, right? So this minute changes is seasonality. and the changes we are having, the how the graph is moving, right? This is actually, this is a trend in the graph. So in this graph we can say that our model is finally able to predict a trend in the graph, but still this model is not so smart enough to predict the seasonality in the graph. We have got, we have minimized the error, but there is still a lot to do. So the question arises, how to now how to predict the seasonality as well as trends in the graph, and how to minimize the error. So if I will ask you question, if I ask you, we we can we can easily, we can observe that there is a huge accuracy difference between a time series modeling and the previous two models which we use. Now, why we are getting this this accuracy jump, right? So I will tell you about why and how our time series modeling is getting such a high accuracy jump. It's because time series modeling is not considering each input as a single input or independent input. It's considering input as a sequence. To explain you this concept, I will explain you with a simple example. If I will give, I will give you a position or image of a ball. If I will give you an image of a ball, can you tell me what's the next position of the ball, or in which direction it will move? No, right? But in case if I will give you a trajectory of a ball, then you can easily say me what will be the next position of the ball, right? So the similar is happening when we are considering stock prices. Our stock prices is a series of sequential data, and the moving average as well as linear regression is taking each date as an independent data. Whereas in time series modeling, the input is sequence of data. So that's why we are able to predict a trend in the graph. But still there is a lot of error in this graph. To overcome this error, we will now use the concept of deep neural network. And such a deep neural network model is and one of the deep neural network model is LSTM. LSTM stands for long short term sale. It is basically a recurrent deep neural network model with some enhancements. But to explain you the concepts of LSTM, I will recap you the basic concepts of deep neural network. What's a what's a simple linear deep neural network? What's a simple deep neural network model? So a simple deep neural network model is nothing but a, a, a is nothing but multiple layers, right? Multiple layers of input, hidden, and output. So what deep neural network does is takes input and gives us the output. In simple mathematics, we can say that a deep neural network is nothing but a differentiable function which takes input and returns us the output, right? But the question arises, how does this deep neural does so? How does deep neural network learns this algorithm that if we will give some input, then it will returns the output? So I will briefly tell you about how deep neural network does show. So we are giving some input to our model. It's predicting output, right? Now our neural network model will find out the error in the model. There will be some error, right? That error will be output minus input. Now this neural network model, so this is the using this error, we will calculate a error function, or in simple, in machine learning it's called cost function. Cost function is basically which it demonstrate the error. So this is the y predict minus yi, which is y predicted output and yi is input. So our aim, if our model can, if we reduce this to 0, then our model is giving correct output, right? So our aim, the aim of the deep neural network model is to minimize this error. So, to minimize this error, what deep neural network model does is use a technique called gradient descent. And a gradient descent is nothing. In simple mathematics, if I will tell you, if we have been given a function and we want to find the minimum of the function, how you will find it? You will use derivative of the function, and using that we can find the minimum of the function, right? So gradient descent is nothing. It's basically a partial derivative of the cost function. But let's not delve into mathematics too much. We just have to know that to minimize the error, deep neural network model uses a gradient descent technique. And once we have calculated the gradient descents, all weights and biases will be updated. And then after each iteration, our model gets more and more accurate. So, but but even this neural network is not capable enough to do the stock prediction. So if I will ask you why, it's the same answer. It's the same answer which we have, which it's the same problem which we have between a moving average and the linear regression model. In the simple deep neural network, we are giving inputs. Each input is an independent entity. But here we have a series, and we have to consider the utmost importance is a sequence. So the utmost importance is of sequence. So yes, it's y predict minus y known, but here we are calculating root mean square error. So root mean square error is square of the error, which is y predict minus y known, and then to, calculating the mean, which means dividing by n, and then finally finding out the root. So this is the standard error function which we use. So there is a reason behind why we use this. Why there is a mathematical reason why we use this function, but let's not delve too much into mathematics here and have a look on the RNN model. So as I was telling you about, that even this simple neural network model is not capable enough of predicting the stock prices, because it is considering each input as a single entity, but we have to give a sequence of inputs. And there exists such a model called recurrent neural network model. This recurrent neural network model is used whenever we have a sequential data. But even this recurrent neural network model have some problems, which is called vanishing gradient and exploding gradient. As I told you that we use deep neural network learns by the method called gradient descent. But what if this gradient descent is not good enough? Then our model will not be able to run. So now Srishti will explain you about what are these problems clearly, and the RNN structure more briefly, give more description about the RNN. And these problems are overcome by the LSTM. Now handing over the session to Srishti. Yes, Srishti, you can start screen share.
Okay, so is my screen visible?
Yes, it's visible.
Okay, so hello everyone. I'll be talking about LSTM. So LSTM stands for long short-term memory. It's a special kind of recurrent neural network used in the field of deep learning. Unlike standard feed-forward network, LSTM has feedback connections. That is, a particular cell learns from its previous cells. So it can not only process single data point, but also the entire sequence of data. LSTM is able to store past information that is important and forgets the information that is not important. So we can see LSTM is also like a RNN, the chain-like structure, but it has some additional computational features that we'll discuss later, which makes it better than RNN. So the question arises, why LSTM? So first is LSTM is capable of learning long-term dependencies. Sometimes we have to look at the recent information to predict the current output. In such cases, RNN works fine. But when the gap between relevant information and place where it is needed is more, LSTM comes into the picture. For example, you can see sentence 1 and sentence 2, right? So if we are trying to predict the last word in this sentence 1, the cloud are in the dash. We don't need any further context. It's pretty obvious that the next word is going to be sky. Consider trying to predict the last word in the text. I grew up in France. I speak dash. So recent information suggests that the next word is probably the name of the language. But if we want to narrow down which language, we need to uh, get the context of this France. So here RNN fails and LSTM comes here. And LSTM also overcomes the vanishing gradient problem, which was mentioned by my friend Prateek previously. So going next, vanishing gradient problem. So what is gradient? Gradient are the values used to update a neural network weights. And vanishing gradient problem is when the gradient shrinks as it back propagates. So the gradient becomes less and its effect on the new value becomes very less and so minimal that the new value is approximately equal to the old value. So here you can see the equation, new weight equal to old weight minus some learning rate into gradient. We can consider this learning rate as some constant for now. So as we go to the previous cells, the gradient becomes so less, so it doesn't affect the new weight much. So in recurrent neural network, layers that get a small update stops learning effectively. Coming up next, here we can see LSTM overcomes vanishing gradient problem. They have additional internal mechanisms called gate, which we'll see in next slide, that regulates the flow of these information. Okay, so here we have the structure of LSTM. So first thing is, this is the cell state. This is basically the memory of the cell. This is forget gate, this is the input gate, and this is the output gate. So the cell state acts as a transport highway that transfers relative information all the way down the sequence chain. It is common for all the cells. This is the forget gate. This decides what information to keep and what to get rid of. So the important information is kept inside the cell and the information that is not important is thrown away. This is the input gate. It decides what value to update and what value to keep as it is. So, and this is the last gate. This is the output gate. This decides what what values to output based on input and the memory of the block. So we have basically 4 main steps to build a LSTM model. First is define the network. We are using LSTM for this. So this is a small snapshot of my code. I'll be showing you the whole code later. So here we are defining the network. So first step is we are making a sequential class, and in this class we'll be adding 4 layers, 2 LSTM layers and 2 dense layers. So first layer I'm adding is LSTM layers. It contains 50 neurons, and return sequence is true here, which means I'll be adding more LSTM layers. And as it is the first layer I'll be adding to sequential, it is important to specify the input shape. So I'm specifying the input shape here. I'm adding 1 more LSTM layer and 2 dense layer. So as we know that LSTM requires 3-dimension input. So what are these 3 dimensions? Is sample, time steps and features. So samples are total number of rows in the data. Time steps are the number of past observation that we use to learn. And in our case, we'll be using last 60 data values to predict the current data. And feature is the number of columns. Next comes is compile the data. This is basically a pre-compute step for a network, and it takes 2 parameters. One is optimizer and loss function. Our optimizer is Adams and our loss function is mean squared error. So the optimization algorithm is used to modify the weights, and loss function, by the name it is clear that it is used to compute the error. Next comes is fit the network. By fitting the network, we can simply think of it as a training the network. So here it is trained using the back propagation algorithm and the optimization algorithm that we have specified earlier. So my batch size is 1 and my epoch size is 1. Here we can see batch size is total number of training examples in a single batch, and epochs is the number of iteration that will be happening on a single data set. So epoch is 1, so we'll be having only 1 iteration for our data set. Next and last step is predict the network. So we make the predictions on a data set. This is so simple. Simply we can call the predict function. Everything is inbuilt. We don't have to specify anything. So, and after the prediction is made, we can apply RMSE, that is root mean square error, to find the error. So okay, so these are the major 5 steps which every machine learning model follows. First is gathering the data, second is preparing the data, model selection, training and predictions. So let's have a look at the code. Okay, so is the code visible? Okay, moving further, let's first understand the problem statement. In this, we are predicting the closing stock price of a corporation, that is Apple company here, using past 60 days stock prices. So we are importing few libraries for this model, which will be using say math, pandas, numpy, some keras, layers and models, and matplotlib for visualizing the data. First steps comes here is gathering the data. So what we are doing here is we are taking the stock price for Apple, and our resource is Yahoo Finance, and the date specified is this thing. Start date is 2012 January 1st, and end date is 2019 December 17th. So this is our data frame we got. Data frame is basically a two-dimensional tabular data structure. Here we have our data frame. Okay, so we can see we have 6 parameters here: high, low, open, close, volume, and adjacent close. So we can see this is the date-wise data we got from Yahoo Finance. If we print the shape of our data, we see there are 2003 rows and 6 columns. Next, we will plot our data. We'll plot close price versus the data to see how the close price is varying by time. So we can see this is very interesting graph here. We can see the price is increasing by years. So we can see how the price is varying as the years are getting here. So next is preparing the data. As we have decided that we'll be taking only the close price to predict the data, so we'll be filtering our data and we'll take close as the parameter. Here we are converting the values, this array into a numpy array. And what we have decided that first 80% of the total data will take as training data and rest 20% will be taking as testing data. So this is trained data length, that is 80% of total data set. So which comes out like 1603 rows. So next we are scaling the data. So the question arises, why do we scale the data? Because most of the times your data set will contain features highly varying in magnitude, units, and range. Min-max scaling brings the values between a specified range. So here we have specified a range as 0 and 1. So our data will be mapped from 0 to 1. This is our scaled data. Coming up next, we are creating the training data set, that is first 80% of our total data set. We have X-train and Y-train here. So basically what is X-train and Y-train is, in X-train, this is the independent variable, that is the data that is used to predict the prices, and Y-train is Y-train is dependent variable, that is the target variable which we want to predict. So what we are doing here is we are making X-train and Y-train. Here I'm as we have decided to use for last 60 days data to predict the current day data. So here after first iteration, I am printing the data so that I can explain you more clearly. Here after first iteration, my X train is this thing and my Y train is this thing. So in X train I have appended the close price from day 1 to day 60. Here day 1 to day 60 I have appended in X train, and Y train contains the 61st close price data. So to predict this, I am using last 60 days data here. So this is how, as the pass through increases, as the iterations increases, the X train and Y train gets appended. Now here in next step I'll be converting into numpy array. Then I'm converting it the X train into 3D. As I have explained earlier, the LSTM model expects the input in the form of 3 dimensions, and these 3 dimensions are sample, time steps, and features. Time steps, this is 60 because we are using past 60 data. Features is 1 because we are only using the close price to predict. So we have kept 1 here. Next comes this model selection, which is LSTM. We have seen the snapshots in the slide. How do we make the model? We are adding 4 layers in it, then compiling it and training it here. So it takes few minutes to train. So that's why I have already trained it. And next comes this test data. So a new data array containing values from scaled dataset 1543 to 2003. Similar to the training dataset, we are making 60 batches and appending it. Y-test contains the last 20% of the total dataset. Okay, so here we can see X-test, we are converting into NumPy array, reshaping it, and predictions. So here predictions are made, and now we are comparing predictions and Y-test values, and we are calculating the RMSE value, root mean square error. So it comes out to be 9.94%, which is quite less as compared to the other models that we have seen earlier that Prateek has told us. Now we are plotting a data. So this is our data. We can see how the accuracy has increased. Like in previous models, it was not even close. So this, my orangish data is the actual value, and yellowish data is my predicted value. You can see there are some variations, but the results are almost close. So here we are coming to the end slides. Here what we are doing is we are predicting the data of 18th December 2019. I have not fed this the data of this date to my model, and I am trying to predict the data of this date. So I am following the same steps which we have done, making a data frame, taking last 60 days, transforming it, testing it, and finally comes out that my predicted price was 261.0426. And when I actually take the value of that date, I get it as 279.73990. So the difference is 18.697. Still the predicted and the actual price is so close. So this is how my LSTM function is working. So do we have some questions?
You can ask us doubts if you have any.
So there is a question here. You can read it out, Srishti.
Yes, sir.
So the question is why you ran only one epoch. More epochs would have decreased the loss further.
We can try that to, we can change our epochs and batch size, and we can see what gives us the least RMSE.
You can check some question. There is another question there. You can check it out.
Okay, yes, this is predicted day wise. Okay,
Date
so
wise to be more precise.
we have one question. Can you predict, can you please explain again what X-train and Y-train value contains? So my X-train value is independent value, and Y-train is dependent value. X-train contains the value 1 minute. Okay, here. Extreme contains the value which is used to predict the data, and white range contains the target value. That is the value which will be getting predicted. Does this clear your doubt?
Okay, any other questions, folks? Okay, so we don't see any further questions. So thanks, Srishti and Prateek, for an excellent session. We hope the audience enjoyed it. Thank you all for attending and your questions. So thanks to Srishti and Prateek for an excellent session.
Just a minute, sir.
Prateek, there are some questions in the questions window.
I'm not able to see the question section where it has gone. Just a second, sir.
You can scroll down in that questions window.
View.
Okay, I'll repeat the question. Can we do bias and variance error check on LSTM models?
Yes, sure, you can use. Error is just a variable you are using to predict, to check the accuracy we are getting. You can check it using the RMSE value. You can check it using bias values.
Next question is, are we checking seasonality here?
No, we are not checking the seasonality. Seasonality is checked using the time series modeling. But in the LSTM model, uh, it works on the basis of the memory cells. So the seasonality is basically checked using the time series modeling like Profit and Sarima.
So let me add one point here. So beauty of or the power of LSTM is that it will automatically take.
So you are not audible.
Am I audible now?
Yes, you are audible now.
So the beautiful part about LSTM is it will automatically take care of any kind of trend or seasonality. That is the power of LSTM. We don't have to account for seasonality separately, as in case of traditional time series modeling. There is another question here. What will happen if time series data contains white noise? Will LSTM work here? So you may have to clarify what do you mean by white noise? Whoever asked that question. So what do you mean by white noise in time series? So LSTM is extremely powerful, I believe. It will take care of a lot of noise filtering or seasonality or stationarity or non-stationarity. Okay. There are some more questions. Prateek, can you see the questions?
Yes, I'm going. I'm having you. Which questions are what? Which one is a new recording?
So the question is how you can handle the news that are affecting the share price abruptly. So we have a Google API bot which will take care of it. We'll try to integrate it with that also, which can classify it into the positive news or negative news.
So if we were to talk about the current pandemic, when it happened in March. So from what I understand, LSTM or any time series cannot predict this kind of pandemic. Okay. To predict this kind of pandemic, you will have to model a lot of environmental and epidemiological factors into the model. But based on time series alone, you cannot predict black swan events like the current coronavirus pandemic. Okay. That requires epidemiological models as well as environmental models built into the input features over, let's say, 20-30 years. I mean, the best of scientists in the world could not predict the current pandemic and the resultant stock price movement. So there are some more questions, Srishti. Can you see them?
Yes, sir. The question is, what is the minimum data size to perform prediction? So the data size can be anything, but more the data, more will be the accuracy. So in LSTM, we generally give huge data because it is a long short-term memory. It learns on long-term basis. So more the data, better is the learning.
No. Okay. Any other questions, folks?
Also, I want to add a point to the Srishti's answer. So minimum data size, as you have asked. So the point of LSTM is to uh, RNN. LSTM is a modification to RNN. So if we want, RNN can't take long sequences as input, and by that I meant that RNN takes small and it overfits the model in the small data sets. If let's say, as a previous example, that I am in a France and I speak, so if I want to predict the next word, I will have to look on the whole previous data set, right? So if I will set my window size to only 3 words or 4 words, it will not be able to predict the next word accurately. And moreover, in recurrent neural networks, if we increase the data size, then we have a problem called long-term short dependencies, which an LSTM can handle. So if in case here we are using 60 days past prices, if we will feed the 60 days past prices in the RNN network, then we will get a RMSE very high. So the point of using LSTM is to increase our data size to perform the prediction. I hope I was able to communicate and answer properly.
Okay, any other questions, folks? Okay, so I think that's about it from the audience I can see. So thanks again to Srishti, Rathi and Prateek, Aryan for an excellent session. And I guess we'll see you in our next set of webinars. Thanks for joining today. Thank you.
Thank you, sir.